Good morning, everybody. For the Friday right before Thanksgiving break, I'll do the best I can to try and keep this short, sweet, and to the point. Wanted to just kind of talk a little bit about some of the history behind our understanding of the motion of planets and kind of connect some of the dots. I think the last time we talked about history, we were starting to get into Nicholas Copernicus and how his theories and his work on heliocentrism sent big waves through the world of astronomy as it was back, just after the Dark Ages and getting into the Renaissance. On your Google Classroom in the stream, I've put up a copy of the slideshow. You might not want to save this just yet because I'm going to keep building on it and probably continue on this track a little bit after Thanksgiving break. But I wanted to talk a little bit about our understanding of orbits and then a little bit in gravity. You had a short PhET lab yesterday where you played around with some orbiting bodies with like the sun and the moon and satellites, and I hope that was fun. I hope you enjoyed playing God and killing hundreds of unsuspecting virtual people by like slingshotting them into the sun and stuff like that. What we're going to do is we're going to talk about the three laws of planetary motion and where those came from and what they actually mean. And we talk about two ancient or not really ancient, but we talk about two old astronomers. We talk about Tycho Brahe and Johannes Kepler. And we've mentioned them before in some of our discussions about history. Brahe got himself made the official royal astronomer. I forget what the country was. I'm not sure if it was Denmark or Holland, but you can Google that if you really care. And so he got himself some serious royal patronage, and he built himself what was at the time the most state-of-the-art astronomical observation station on a little island just off the coast of the country he was working in. Basically had the thing to himself. Now this is before telescopes, and so all of his observations he made by eye, but he made these absolutely gigantic devices for measuring angles just using the naked eye. And he spent about 20 years making very detailed observations of the movement of the planets, the movement of the sun, the movements of the moon, just night after night, 20 years worth of observations. What he was hoping to do, he was hoping to find some mathematical proof that would back up the Copernican model and kind of throw shade on the old Ptolemaic model that had been used for hundreds of years before that. But his math wasn't all that great. He also had a falling out with some of the royal family and ended up getting himself booted out of court. He went to work somewhere else for his last few years of life, and he got himself a lab assistant, a young guy named Johannes Kepler. Actually, he was about 30 years younger than Brahe, 25, 30 years younger. And he brought him on board, and at first he didn't want to give him very much of his information. He kind of spoon-fed it to him a little bit and said, here, take a look at these numbers and tell me what you can make of it. And so Kepler worked with what he could, but Brahe was afraid that Kepler was going to get all the credit and all the glory for all this stuff if he just flat out gave it to him and said, hey, go to town. And then a year later, Tycho Brahe up and dies. So then Kepler has access to all of it anyway, and Kepler spends the next 20 years or so looking at all of Brahe's numbers and all of his data and trying to find some mathematical formulas that would make sense of the motion of planets. One thing that he figured out that was kind of the key to his understanding was analyzing the motion of Mars. He figured out that Mars's orbit around the sun was not a perfect circle. It was decently close, but he noticed that there was enough repeated variance to it that the orbit was actually an ellipse. And that right there was the key that he needed. He knew that once you got rid of the old idea that the heavens were perfect spheres circling, forever, then all of the observations kind of lined up. So he ended up publishing his first two laws of planetary motion in 1609. Did I already mention it took him about 20 years just looking at all these numbers to come up with this? So, he stayed on task. I guess, I don't know. I'm sure he took bathroom breaks, but the first law of planetary motion that he came up with is that the orbits of all planets are elliptical. Here off to the side, we've got a cone sliced in several different ways. If you slice a cone in a way that's perpendicular to its major axis right there, you get a circle. If you get one that starts on the side and ends on the side like that, you get an ellipse, and that's the shape that we're talking about. Of course, then you can also derive a parabola or a hyperbola from that. But the ellipse, he found that even our own orbit, although it's very, very close to a perfect circle, it is just barely elliptical. And every moon that he observed, every planet he was able to observe at the time that they knew about, had some kind of elliptical orbit. Now, an ellipse is a little bit different from a circle. Instead of having a center point, you've got two, what he called foci. It's the plural of focus, but you've got two foci that the ellipse is sort of based around. One of the foci in an ellipse for a planetary orbit is the sun. The other one is just a point in space. His second law came after this first one. He imagined that if you took a planet and you could take a stretchy rubber band, some kind of a stretchy line, and tie that planet to the sun, then as that planet moved through its elliptical orbit, that line would stretch and shrink. And as that planet moved through its orbit, it would sort of trace out a pie-shaped wedge of that elliptical orbit. He noticed that the planets moved much more quickly when they were close to the sun, and much more slowly when they were far from it. And so he figured out that if you were to take the elliptical orbit like we see right here, and if you were to use that imaginary line to trace out a region of space that it would cover, that the area of that region of space for equal amounts of time, no matter where you measured it, would be equal. And so if you see close up in area A, when the planet is far away from the sun, it's not moving very quickly. And so the arc that it traces out is very, very small, but since it's so far away, you've still got area A in here that would get shaded in. When it's much closer, like you see in B, for the same amount of time, it's moving much more quickly, since it's close to that focal point of the sun. But since it's closer, the line is shorter. So as it traces this out, it would end up shading in this imaginary area. And if you look at, and I'm not going to do so, but if you were to calculate the amount of area in that ellipse that was covered, the area of A equals the area of B. And that's true no matter where in this arc, or where inside this ellipse you would measure. For an equal amount of time, so this time right here is equal to this time right here, the area that it would cover up would be equal. Now, I said there were three laws of planetary motion. The first two he came up with, but it took him, I think another 10 years to come up with the third one, because he wanted to find some mathematical relationship between the orbit and the time that it took something to orbit the sun and its distance from the sun. And he played around with it for a good 10 years, and finally he chanced upon the third law. And the third law basically says that that the planet's orbital period is directly related to its distance. And let me kind of decipher these pictures here for you. We are going to call P orbital period. Okay, that's just how long it takes for a planet to go completely around the sun. So for us, our orbital period would be 1 year. For other planets, it's going to be either more or less than 1 year. But you take the orbital period and you express it in years. The semi-major axis, what they're talking about right here, if you measure the widest point across an ellipse or across an elliptical orbit, and then you take half of that, that's what's called the semi-major axis. Now, interestingly enough, that distance is also the average distance of that planetary body from the sun. Okay, so let me go back a slide. So if you were to measure from this side of the ellipse all the way across to this side of the ellipse, and then take that and half that distance, then the distance, say, from here to here at the edge is equal to the average distance that this thing would be from the sun at any given time. Okay? So think about what you know about the Earth. The distance between the Earth and the sun is 1 astronomical unit, 1 AU. Now he found even more so that if you express a planet's orbital period in years and you express its semi-major axis in AU, then it perfectly fits this equation right here. That if you square its period, that's equal to its semi-major axis cubed. Okay? I'm not sure if I've got any more slides. I do have one more slide, just kind of summarizing everything. But I want to show you the summary slide, and then I want to take a look at some planetary data, and we're going to see if planetary measurements actually line up with Kepler's formula here. One thing, I don't know how many of you watched your way through all of the Privileged Planet, but one thing that stuck out to me in that video was how all of these laws and all of these constants and all these relationships in the universe, as big and as complex as it is, can really be boiled down to very, very simple math. And I know, your first instinct would be to look at this and say, hey, that does not look like simple math, but it really is. I mean, you can type that out with 5 characters. That is not a big complicated formula. So just in summary, here's the 3 laws of planetary motion written out in their entirety. I kind of gave you the Cliff Notes version of those. And you can go back and you can take a look at this slide in the slideshow anytime you'd like to. But yes, I am going to expect you to know or at least be able to explain these 3 laws using your own words, or illustrate the 3 laws using pictures. So I think, yeah, that's my last slide. So let me exit out of the slide here. It'll let me. Boom. Okay. Now I've got pulled up right here a data table that's got some of the semi-major axes and the orbital periods for the planets. Can I zoom in even more? I bet I can. Let's see. Maybe. There we go. All right. So what I'd like to do is I would like to, let's just pick out one of these random planets. Now Earth, that's easy. If our relationship is p squared equals a cubed, well, 1 squared is going to be equal to 1 cubed. Okay, so we're not going to use that as an example. I want to look at some of these other ones. So I'm going to throw it out to you in the chat. The first 3 planets that I see y'all type up are the ones that we're going to take a look at to see if we can confirm this. Go ahead. And nobody's typing. Yay, class participation. All right, somebody either type up a planet or I'm going to boot all y'all out of here and say you never showed up. How about that? Yes, I can. Hey, there's a vote for Venus. Cool. All right. Don't be obscene. And let's see, one more. All right, so we're going to go with Venus, Uranus, and Neptune. And we're going to see if we can confirm the p squared equals a cubed thing that that Kepler came up with. Okay, p squared equals a cubed. Okay, where p is period and a is, yeah, semi-major axis, or average distance from the sun. So let me go ahead and get some numbers down for that so that I can zoom in. For Venus, P, A. Oh, I zoomed in too much. Okay. Orbital period for Venus in years is 0.6152. And its semi-major axis is 0.7233 AU. Okay. For Uranus, its orbital period is 84.01, 84 years. And its semi-major axis is 19.1914 AU. And then Neptune, way out there, is, did I write, oh, no, it's down here. Okay. Neptune is, holy crap, 164 years, 164.79. At least we've got a nice variety of numbers here. You guys picked some good ones. And it is 30.0611 AU. Okay, so now I can zoom in a little bit where we can actually see things. So if they're saying that p squared equals a cubed, let me get my calculator here where y'all can see it. Maybe a little more light. That's better. Okay, so let's start with Venus. Let's take 0.6152 squared. Let's see what that gives us. Oh, I guess I could put the calculator back down. 6152 squared. I get 0.378 and change, okay? So 0.3785. Okay, now let's take the cube root of this. Let me see. Do I have a cube root button on here? I sure do. Cube root of my answer. I get 0.7233. Oh crap, look at that. Okay, so Venus checks out. Boom. I'm not going to say let's take a look at, but let's consider Uranus here. So we've got 84.01, so let's do 84.01 squared. Okay, I get 7,057 and change. 0.68. I guess I should actually finish up my whole thing here. And if I take the cube root of this, then I get the 0.7233. So now let's take the cube root of this guy. So shift cube root, answer. I get 19.18. That's awfully close. Would you agree? Super duper. Okay, so 19.18 AU. Cool. And then Neptune. I have a feeling that this is going to also prove true here. You know, otherwise somebody would have discredited this a long time ago. But just for argument, let's do 164.79 squared. Nothing more fun than watching somebody put numbers in a calculator on the internet on a Friday. So I get, wow, 27,000 and change. So let's do 27155.74. Okay, taking the cube root of that, I get 30.0. Okay, so let's take the cube root of that. I'm shooting for 30.06. Cube root of my answer, I get 30.057. Ah! Dadgum, that's close. I am super impressed at that. I'm so glad that worked. 0.0575. So there you have it. We've got mathematical proof that Kepler's third law is a thing, and it totally works. So I will leave you with that nugget of fun today, and I hope everyone has a very happy Thanksgiving.